Welcome. In this session we'll cover what a caliper, also called a geometry, pig does, how it senses pipeline shape, and how we turn those readings into inspection outputs you can act on. I'll tie the concepts to planning, execution, QA/QC, and reporting, so by the end you'll know when to use a caliper run and how to interpret dents, wrinkles, ovality, and bends for integrity decisions. Here's the roadmap. First, a quick definition of a caliper pig and its sensing principle. Then we'll walk through components, arms, rollers, odometers, IMU, and what each contributes. After that, we'll look at features detected, how data is processed, and what the limitations are. We'll finish with safety, standards, and reporting best practices. A caliper pig, also known as a geometry pig, is an inline inspection tool designed to measure and record the internal geometry of pipelines. It uses spring-loaded arms or fingers equipped with contact rollers to sense variations in the pipe's internal diameter. These arms deflect when encountering changes in the pipe wall, and the deflection is measured using sensors such as potentiometers or encoders. The tool is capable of detecting dents, wrinkles, ovality, and bends, and can provide indirect indications of significant internal corrosion when geometry changes are pronounced. Caliper pigs are commonly deployed for baseline surveys, post-construction checks, and pre-MFL or magnetic flux leakage or UT or ultrasonic testing readiness assessments. They do not measure wall thickness directly but help identify areas where further investigation may be required. Their data is crucial for pipeline integrity management, as it allows operators to understand deformation patterns and plan maintenance or remediation activities effectively. The sensing principle of a caliper pig revolves around mechanical compliance and precise measurement. Spring-loaded arms extend radially from the pig's body and maintain contact with the pipe wall. As the pig travels through the pipeline, these arms deflect in response to changes in internal diameter, such as dents or ovality. The deflection is recorded by sensors, and axial position is tracked using odometer wheels, while optional inertial measurement units or IMUs provide curvature and orientation data. The system comprises mechanical components like cups or discs for propulsion, centralizers for alignment, and bypass valves for pressure control. The sensing system includes arms, rollers, and measurement devices, while navigation relies on odometers and IMUs. Electronics such as data acquisition units, batteries, and memory modules ensure continuous data logging throughout the run. Together, these components enable accurate mapping of pipeline geometry and identification of anomalies that could compromise structural integrity. We'll focus on what features are detectable and how we interpret them. The goal is to translate raw radial measurements into actionable integrity findings with consistent terminology and parameters, depth, axial length, circumferential extent, and clock position. Caliper pigs detect several critical features that influence pipeline integrity. Dents are inward deformations that can occur due to external impacts or construction activities. They are characterized by depth, axial length, circumferential extent, and clock position. Wrinkles are short pitch ripples often found in bends, typically resulting from buckling during installation or thermal cycles. Ovality refers to the difference between maximum and minimum internal diameters, expressed as a percentage of the nominal diameter, and can indicate cross-loading or improper burial. Bends are assessed by calculating the pipeline centerline curvature to determine bend radius and angle, which is essential for tool selection and operational planning. While caliper pigs do not directly measure corrosion, significant internal corrosion may manifest as noticeable changes in geometry, serving as a screening indicator for further investigation using advanced tools like MFL or UT. Data interpretation from caliper pigs involves analyzing radial measurements collected by multiple arms arranged circumferentially. Ovality is calculated by comparing maximum and minimum diameters over a defined window, while dents are identified as localized inward deviations from the mean internal diameter. Wrinkles appear as repetitive ripples in the radial profile, and bends are derived from continuous curvature analysis of the pipeline centerline. Each detected feature is reported with key parameters such as depth, axial length, circumferential extent, and clock position. Speed control during the run is critical, as variations affect axial resolution and measurement accuracy. Operators must validate anomalies through field measurements or complementary inspection technologies to ensure reliability. Proper interpretation of these data points supports proactive maintenance and enhances pipeline safety. Now, operations. Planning and execution determine data quality as much as the tool itself. We'll outline pre-run data needs, pig selection, speed/flow setup, launch/receive discipline, and post-run handling and QA/QC. Effective caliper pigging begins with meticulous pre-run planning. Operators must gather essential data, including pipeline nominal diameter, maximum operating pressure, medium type, temperature, route drawings, and bend lists. Pig selection should consider diameter compatibility, arm count, maximum deflection capability, and minimum bend radius tolerance. Cleaning runs using gauging and brush pigs are recommended before deploying the caliper pig to prevent debris interference. Operational parameters such as speed, typically 0.8 to 1.5 meter per second, pressure, and flow conditions must be defined to ensure optimal data quality. Launching and receiving procedures require verification of trap dimensions, kicker line configuration, and adherence to safety protocols. Post-run activities include inspecting the pig for wear, downloading data promptly, and performing preliminary quality checks. These steps collectively minimize operational risks and enhance inspection reliability. Data processing involves validating channel health, synchronizing odometer and sensor data, and filtering false positives. Quality assurance includes checking for signal dropouts, noise levels, and calibration drift. Deliverables typically consist of a feature list detailing anomaly type, location, depth, clock position, and confidence rating. Despite its capabilities, caliper pigging has limitations. It cannot detect external corrosion, and internal corrosion is only identified when geometry changes are significant. Tight bends, tees, and partially open valves pose risks to tool integrity, while speed variability affects axial resolution. Understanding these constraints is vital for accurate interpretation and planning follow-up inspections using advanced technologies like MFL or UT. Safety and standards frame the operation. We'll cover isolation, verification, gas testing, PPE, handling ergonomics, emergency plans for stuck/stalled pigs, and how standards guide acceptance criteria and reporting. Safety is paramount during caliper pig operations. Procedures must include pressure isolation and verification before opening traps, gas testing, ventilation, and appropriate PPE selection. Operators should mitigate pinch point hazards during pig handling and use ergonomic lifting aids to prevent injuries. Emergency response plans for stuck or stalled pigs must be established. Compliance with industry standards such as API, ASME, and DNV guidelines ensures consistency and reliability in inspection practices. These standards define operational thresholds, reporting formats, and verification protocols, aligning inspection activities with regulatory and organizational requirements. Reporting should include comprehensive details such as feature type, location, axial length, circumferential extent, depth, and clock position. Confidence ratings and recommended actions help prioritize remediation efforts. Standardized reporting formats facilitate integration with integrity management systems. Next steps involve confirming pig compatibility for future runs, planning cleaning sequences, defining reporting thresholds, and preparing field measurement tools for anomaly verification. Establishing a structured run book with responsibilities and acceptance criteria ensures operational efficiency and enhances pipeline integrity management.